Yeah, okay, that works better.
Cool. Okay, perfect. So let's get started. Before starting, I want to actually just quickly say thanks to Daniel for organizing this. I mean, he is super welcoming, and thank you very much also TNG for organizing this. It's super nice to see so many faces interested in robot learning, especially here in Munich. So really happy to be here. Small applause as well for you for being here. Cool. So just again about me, I'm Daniel, work at Bogenwigel. I'm an engineer there, and we're also working on robot learning. But today I'm actually presenting some work that we did at the TUM, at the Learning Systems Lab, also with Ralph. I forgot to put the names of everyone else, but Ralph, Martin, Oliver, Max, and Angela Schullich. And today I will just be presenting to you the next minutes. It's going to be kind of like more like a control theory presentation. I think it's a good way to start the Robot Learning Club in this way. So there are going to be a few basics. So what is CRISP? So it's just like an open source package with a set of controllers that are intended for real-time deployment on a robot. They run at 1 kHz, and they are implemented for robots that have like a torque interface, ROS2 control. And the controllers are robot agnostic, so they can be deployed in any manipulator that provides this interface, which are actually a lot, like Franca. We also have like the URs, Duatic, so many of them. And on top of that, we also provided a Python toolbox with Crispy and Christian to make it really easy to interface with the robot, send target commands, and also record data sets based on the outputs of the controller. This presentation is going to be divided in 4 parts. So first, I'm just going to motivate a bit the reason why we started working on this topic. Then I will go a bit on how it works. It is going to be really educational. I also tried something new for this section, so it's going to be quite fun. Then I will talk a bit about the interfaces to the controller, so how it is used and how the data is collected using this. And then at the end, I'm just going to give a few lessons learned from my time at SY, and also trying to deploy models. So it's just going to be a really introduction kind of presentation where we start from the basics. So about the motivation, I started working on this project with the LSY almost already 2 years ago. And at that time, we were really trying to solve the Lego stacking task. And for this task, you really need to control the robot in a compliant way, right? Like when you're trying to stack the Lego, if you go with a robot that is really stiff, it's just going to make the Lego jump or not really work. And the compliance really helps you to get it stuck in. And at the same time, a lot of people in the LSY were starting to work on behavioral learning, especially end-to-end learning. And the models at that time and still now usually output commands of a really low frequency. I think back then you could always see those videos where the robot is like outputting like commands like really slowly. And we were really looking for something where you can just stream commands and you are just going to smoothly interpolate between those. And I mean, these kind of controllers, they already exist in literature and so on, but they were not really super accessible in the community as of then. And that's where it brings me a bit to the second motivation. So with robot learning, we are really moving from this kind of software engineering version 1, where we have like a lot of engineering modules for the robot software stack, right? So previously, for example, if you had your robots, you had usually the stack with ROS2 and so on. you would interact with the environment, and your system will somehow sense whatever is there, maybe make some sensor fusion with some packages like the robot localization, then create a plan. If it's a mobile robot, it will just create like a navigation plan, or for a manipulator, it would be like something with more movement. And the community has already been working a lot on this, right? And there is a lot of work going on, but really we're moving more towards a new paradigm where we don't want to engineer every single module and then interconnect them with some kind of interfaces that we define, but we really just want to put more weights into the planner, which kind of is the policy now, which absorbs most of the perception and the planning, and then output some kind of quite continuous stream of poses or targets, and have a controller that really is kind of like a safety guard to apply those commands and be compliant with the environment, and so on. And we really just want it to be minimal. We don't want like a full planning stack, like move it or whatsoever. We really just want like a controller that satisfies this. And we want it as well to still be part of this community, right? Like where you already have like a lot of robots implemented and working with the ROS2 control interface. So we really wanted to stick a bit with that. So that was a bit the motivation on why we wanted to implement these controllers and making them like available and also showing how to deploy policies. So that was the first part, the motivation. Now let's jump into a bit more like the control theory part of this. And this is going to be quite fun. So I don't know how much you know about control theory, but I'm just going to go like really step by step and doing like some really basic things. I try to make it really simple to understand. So we really want to take the first most simple robot. Let's just imagine like one robot with one degree of freedom, one arm, and we're trying to minimize the error of the desired joint position with respect to the current one. So this is basically this. So the way to do this is like the most classical thing that maybe some of you know is like the PD controller. So we take this error and multiply it with a certain constant. This is going to give you like the stiffness or like how fast you want to minimize this error. And this gives you the control input, which is here the torque. So if you remember from physics, torque is kind of like a force. So if you have like a force is equals m times a, so a force is going to generate an acceleration. And this control law is going to accelerate this arm to go to the Q desired as long as this error is on 0. Okay? It's just going to generate a force, and this force is going to try to move the robot to that position. We also have this term here where we are basically avoiding large speeds. So this is the velocity, joint velocity. So if you go too fast, then you try to avoid going so fast. And that's the bad. Okay. So now for this controller, you could imagine that if you grab the end of the arm and you pull down, you are going to feel a force increasing the further away you pull it from the desired trajectory. Okay. So I think that's quite simple. It has a few issues. And one of those is what would happen if you add gravity. Then the controller is going to bring the Q to the desired position, but the gravity is also generating a torque. So the controller is going to output some kind of torque, and this torque is going to be canceled out with the torque of gravity. And this is in general a problem when you have like this kind of torque or effort-based controllers, that you are going to be really sensitive to unmodeled parameters or terms in general. So if you don't model them and your controller is really compliant, you are always going to have like really large errors when your controller converges. Okay, so this was like the most simple one. It really took a long time to do this. but this is going to make a lot of sense when we go to Cartesian space. So because basically what we want to do the same thing, but now instead of having torques, we want to command a certain force to the end effector and bring it to a certain position. So this is going to the next slide. So we now want to take these robot arms, 3 degrees of freedom, and we have its current position, and we want to bring it to a target. And we can just imagine this, right now it's not moving, but just imagine we want to take the end of this robot and just apply a force and move it towards the target. Okay? So we want to translate this idea of having this force being applied to the end of the robot and compute which torques are necessary on all the joints so that we apply this force to go towards the target. Okay? And there is actually like a really simple formula for this, which is here. So if you want to apply this force to the end effector, you just need to multiply it by the geometric Jacobian transpose. So this Jacobian is basically like the footprint of the kinematic chain. And you can always compute it from the URDF, if you know a bit about robotics. And usually the URDF gives you what is the shape of the robot. And there are like packages that really help you to compute this. Like Pinocchio is the one that we're using really great. So yeah, if you multiply this matrix with this force, you get basically the torques that you need to apply that force to the end of the effector. So that's the magic. Now the only thing that you need to do is decide what kind of force you apply here so that the controller behaves the way you want. And that's where we come to the idea of the Cartesian impedance controller, or also collision space controller. The difference is just like an extra matrix multiplication. It's not too important. But the formula, I'm just going back to this one. So you see you have J transpose times the force. Now it's the same one, but instead of having the force, you have here the error. So the error between the current position, which is the end of the robot arm, and the target, which is the green point. So if you have like an error, this error is going to be multiplied by the stiffness, the same way as it goes in the joints, and then it's going to compute the torques required to generate a force. And we also add to that a damping term, so we avoid the large speeds. And that's it. So it's basically the same scenario that we had before, with one joint and one robot, but now we are basically just computing the error in the Cartesian space or operational space, and we compute it back with the Jacobian transpose in the joint space. And you can tune those parameters to get like a nice response, like the stiffness gain and also the gapping gain. If you increase the stiffness, you are in general going to track better your target, but you're also going to generate much larger forces when you're in contact. Okay? So there is always this trade-off, right? Maybe I want to really fast up tracking, but at the same time, when you collide with something, you don't want to be like too, no, it's not okay. Yeah. You don't want to be like too rigid. So that's like the most important thing. But now to get this controller to run a bit better, you need to add more terms than only that tau. So in general, robots or like our arm itself, you can get to a certain target, a certain position, and at the same time, you can still move your elbow, right? I mean, you all know this. So if you only apply this rule, there is no constraint on how you would move your elbow. So you also need to add that and take this into account. This is usually done with extra terms. So you take whatever we computed before, and then we add an extra term to try to bring the arm to the correct position. And in this case, this is what we call the null space configuration. So we try to bring the elbow to a position which is not awkward. So if I move the arm around, you see it's just going to move in a lot of weird configurations. But if we want the arm to be always more or less in the same posture, we can still have the same end effector position and then try to get to a target home position. So then moving from this position is always less awkward.
In this case, joint 1 and 2, so you start 0, joint 1 and 2 are the elbows, or which ones are the elbows?
The elbow it's a bit hard to see what the elbow is in this kind of robot. If you are like a Franca, you would see it directly. It's like joint 5 or something like this. But yeah, I mean, at the end, you are just like setting like a home position for your joints, and you say, okay, try to get close to that joint position. And in our controllers in Crisp, you're also able to just stream the home position that you want the whole time. So your policy could, in theory, always control the elbow position as well if you wanted to. That's actually, it would be even better because otherwise this degree of freedom is just like, might not the idea, it's not used at all. Okay, and this thing keeps going. So as you can see, you can take those two terms and then add much more, right? Like you can also take the Coriolis forces into account. You can add an extra term to compensate with an extra force. You can also try to avoid joint limits. So you can do all of these things, also add some kind of safety to the torques so that you don't have like a really large torque being applied or torque rate. So really you can add more terms, and we try to make all of these parameterizable so that you can always switch between terms. Okay, so that's more or less like the most important part of how it works. I'm going to skip the next slide because this one is more interesting. So why ROS? The nice thing about ROS is that a lot of people already worked on it. A lot of people already have like these hardware interfaces implemented either from the community or also like, for example, for Franca, it was Franca themselves that they were also working on that. So it was much easier to just say, okay, let's just use that existing interface and just build on top of that. And the controller is just doing that. So it just assumes that it's like this ROS2 control framework. We have the UIDF with Pinocchio, we can pass it, we can instantiate a controller, and we also have like some broadcasters, and then we can easily plug this to a robot and just control it. And then in order to interface that controller, we only wanted some topics, so just making it really easy, stream some values and get some values out of it. And that was really like the most important part. And now there is also, I don't know if you know Pixie or RoboSnack. It's a really nice way of packaging ROS2 as well. So you can kind of start the whole thing, for example, in a Franca, just by running this command. And then it's just like the robot starts, the controller is running, and then you can already like send some commands to it. It's really cool. So that's really what the most important part of the controller. But we also wanted to have like this, we also wanted to deploy policies, right? So we built on top of that a Python interface and a gym. So you can just imagine that the Python interface is like the funnel where either it takes inputs from a human or from a policy and then send the commands to the controller and gets feedback from the broadcasters of the robot and also from the cameras. They are not part of this diagram here. And all of these things are then saved and recorded in low format. So here is also an example of how you would use it. So you would just instantiate make robot. Franca is running somewhere else. And then you wait for the robot to be ready. And once it is ready, you just use it as it was, like just a simple Python code just to move the robot around. And setting targets is nice. So if your robot is not too stiff, it will nicely, smoothly move around. So you can also tune it from here and just helps you iterate fast on this. And one important thing that we decided for Crisp that I want to talk about because it's actually quite interesting and I have seen many different opinions, we can talk also about it, is how to collect the episodes. So like, what is the strategy that you use? So I think there are two schools or two philosophies on how you do it. And one way would be, I'm going to show the other way, the one that we are not doing, is to use simply an async stream and like package everything in a bag, so a ROS bag or an MCAP file, and the data is timestamped with values with different frequencies, different streams, and you take that timestamp data, and it has basically everything, and you just post-process it before you train. Because when you train a policy, you are just training, especially in behavior cloning, you're just taking observations and actions, and you are just trying to fit supervised learning, right? So you're just trying to fit the model to that. The disadvantage of this method is that you need to do the post-processing, and the post-processing is really hard. Like, really, I think it's more complicated than what people think. You can make a mistake there, and then you are going to have a mismatch. So we really went for a more simple way of doing it, and this is just like what I call the synced episodes directly. So in the funnel, when we get an action from the human, and we look at the latest observations, we just know that that's exactly what the policy should learn, right? So if we have like a fixed frequency at which we also want to run the policy afterwards, we just say, okay, this is the observation, latest observation and the action. So this is what I save in my data set, and this is what afterwards the policy is going to output. And since we only have one funnel, this is going to be exactly the same kind of output based on that observation. This has, however, the disadvantage that you are losing data, because you need to decide right at the beginning what is going to be your frequency, how are you going to deploy it. So I'm just showing this because it's quite interesting. I've been like talking with people and they all have different opinions. We decided to go for the simple one. It doesn't mean it's the right one. It's one of the issues.
I don't get it. How are you going to synchronize it?
In which situation?
In the synced episodes.
In the synced episodes.
Yeah.
So like
because your tele-op data is at a totally different frequency than your policy and
actually not. That's the funny thing that we do. We are actually sending the tele-op values at the same frequency than the policy is going to deploy. So we decided already beforehand at what frequency the actions of the operator are going to be sent.
Okay.
So if the policy is running at 10 Hertz, we only send actions at 10 Hertz.
But your 10 Hertz policy is not guaranteed in many cases. So it's like fluctuating often, right? This kind of thing.
Yeah, well, actually, you can really decide at which frequency you want to deploy them. I mean,
okay, you have a generous compute stack, yeah.
Yeah, if you know exactly how long inference takes, you can already like prepare beforehand. I already run 505 at 30 Hertz. It's possible, right?
Yeah, but 505 is small.
True. So that's why I'm saying it's kind of a disadvantage, right? Because at one point, if you really want to go much slower, you will need to either make large chunks, right? Like, because usually you don't output just single actions, but you output a chunk. So you could also do like a sync inference and so on. Then you can also fight all these things, right? It's
and then the stuff of your VLA you run in the cloud makes it.
Yeah. But we can talk about it. Let's just finish quickly, and then we can talk again about it. Maybe there are similar questions from everyone. I'm anyway almost done. So I really just want to talk about what I learned. So it was really the first time that I was open sourcing something and really working on such a big project. And open sourcing it was really nice. Really, it opened like so many doors. Like I open sourced it and someone came, oh yeah, I want to try it on the UR5. And he did it. And then I was like, wow, that's crazy. That's super cool. Like, I mean, I don't have a UR5 at my home or like in the lab. And then later we also tried it on the Dynarm and from Duarte. And it was really great to have this. So I'm really thankful for a lot of the contributors. Not all of them are there. To be honest, there are more. And also a lot of PRs that arrived were really like just adding more to it, like variable stiffness, for example, from Ivan. We also got like an admittance controller. I would have never worked on this, right? So this really just happened from that motivation from everyone to also have on this. So really thankful for that. And really just to finish, I just want to give some takeaways on general learnings that I had during deployment. And I think there are just two, and I think they still hold today. So real hardware evaluation is really the bottleneck. I mean, you see here some videos of myself evaluating different policies and the different parameters and so on. It just takes too long. It just takes so much time. It's just so painful. And of course, you could do everything in simulation and so on, but then you optimize for simulation and you never deploy on the real robot. And then on the real robot, it doesn't work the same way. And that's always a kind of trade-off, right? So I still think that here there's a big bottleneck. Also, the setup changes, right? Like your colleagues come and they move the camera and you're like, oh, why did you do that? It's like, I think some of you already experienced this. And data collection is probably one of the most important things, right? Like good data makes almost most of the difference. So I was working on the Lego task and we were getting like a success rate of 20%. And just by slowly fixing a few bugs and then just making proper demonstrations, you just get to 80%. I mean, there is no magic. You just need to do the demonstrations properly, like consistent, and then it's just going to work. The demo is going to work. It's going to be quite, let's see, how do I say that, overfitting in a lot of situations and so on. But it's just going to work. And really having the good data is key. So really, those are the two biggest learnings that I really had during my time. And that's it. Thank you, everyone. I don't know if I think we still have time for questions. I think I took longer than expected.
Yeah, there's either one or two questions, and then we'll take it